so going back. But that's good. Yeah, I can see it. So, what do I want to tell you? I think that the mathematical aspect, this will be the same for the last time, because this introduction we have to start. But the mathematical aspect is supposed to be different. So this is what I'm going to do. Why do I say what is cyber? Because we are using the word cyber all the time, and we don't always have definition what is cyber. Even a computer science major might not know the definition for. Do you have a definition for cyber? You see? So we need a definition for cyber. Mathematicians, we have to define everything. We are not leaving anything vague. We know everything. So what is cyber? Cyber words include everything which is on the virtual world. So we define it by non-existing, all the things which we cannot touch. So on computers, on chips, on wires, on non-tangible entities. And someone might say that eventually you touch it because you not touch it because it's tangible, because there's some wire, some electricity goes from one place to another. But things that what is on the virtual world. So this is the cyber. And when we talk about cyber, then in particular, what is everything that is on the virtual world? So everything in our individual normal life, so many things in our life. So if we switch a light or we find a train schedule, I gave all these examples here. Recalling our lab results from the laboratory, or saving money. I mean, we save money. We don't really have money. What do we have? We have a line in some bank account, and this line that in the past there used to be, for every line there used to be dollars in the bank. So they don't have dollars anymore. It used to be that for every dollar there is some gold in the American government basement somewhere in Washington. They don't have it anymore. So money actually doesn't exist. It's a line. That's why Bitcoin, people say, no, Bitcoin is no good. There is no money behind it. But also the regular money, no money behind it. So everything is virtual. And all these other examples that I'm putting it, if we try to open Waze for GPS, everything is virtual. A lot of our things are virtual. Even shops now are virtual, right? You don't go to the shop anymore to buy something. But if I look at the society in general, also the society in general, everything is actually on the virtual world. So everything that I mentioned below here, I say we switch a light in the house. There's a power station that is transportation design and operation, and also air traffic and health system and data management and stock exchange and cellular networks, Google, weather forecast, navigation system, earthquake. What I did in the first paragraph, how it affects me, but it's part, what affects me or you, it's part of a big system. So cyber is so much more. So why is cyber extreme risk phenomena? Why do we need cybersecurity? We need cybersecurity for three reasons. There are three levels of threat. Most people think the problem is that someone will know our secret. That's the smallest problem of all. If they know your secret, if you're a criminal or if you hide the money from your wife or something, then, but it's not really a problem. They know your medical devices, your medical, okay, you lose privacy. The problem is that we lose the ability to operate the system. So we cannot operate the electricity of the city. We are losing all the executive tools to design, to control, to forecast. So there was an issue about losing control of the electricity in New York about 20 years ago. The city was shut down for 2 days. It's terrible. And you know, if you're losing the information on health system before an operation of a person, that's also very bad. So it's not only what the bad guys know about us, it's also that we don't have our information. That's the second level. But the worst level is that someone else operates our system against our well-being. They're stopping all the cellular. They're stopping the electricity. They push on the red button, they, they push on the red button that operate the nuclear arms. So there are many, many things that the bad guys can do for us if we don't have a good cybersecurity. So you knew before, but now you have maybe more wording. Why is it so important to have cybersecurity? And without saying much, this is a list of things that might happen to us as a society if a hostile entity takes over. In the subway, they just make two subways come into each other, and then it's a major disaster with a lot of casualties. Of course, we're always afraid two airplanes coming together, or the cellular network collapse. It's also life-threatening because you count on the cellular to give you information, to help you with e-medicine, with taking a baby from somewhere, so no cellular. It's of course the monetary system, then everything we saved is gone. Weather forecast is also important because if it's manipulated, airplanes or boats will go in the area that is bad for them, and there will be also casualties. This is the example that I said before about electricity. So it's clear that cybersecurity is a national security. But it's not only the data, it's important to mention again that its infrastructure and civil data are critical to keep them. As I said, all the infrastructure. So it should be a major goal for governments, industries, and the individual. And in the base of all cybersecurity, it's mathematics. Sometimes you don't know it. You think maybe it's computers, maybe it's engineering. It's also this, but in the base is mathematics. And we'll get to that. So what are the challenges in cybersecurity? So there are 5 challenges. Organizational challenges, societal challenges, psychological challenges, engineering challenges, and then we come to mathematical challenges. Not because it's less important, because it's more important, so I want to give it more time. So what are the organizational challenges? Data is not produced by a person. Data is produced mainly by organizations. So it can be government organization, it can be health system, it can be civil organization. They are creating the data. So, and the data is leaking from the organization through the weak points. So the organization can have a lot of security around the rules and regulation and protecting their data, but they might have one guy in the organization who likes to shop online when he's in work. So through this guy, the bad guys can come in. So you have to find out the weak point. It's like in physics. You have a ball. If there's one weak point, then that's the place where the ball will blow up. So we have to have we have to understand where is the problematic. So that's just few words. I mean, there's many organizational issues. I know a startup company in Israel that developed technique to identify the weak people in the organization. So of course, when they interview them, they are going. I told you before about the hedge fund. So some people from the hedge fund wants to come and give lectures about hedge fund because finance mathematics traditionally was investment banking and other stuff, not hedge fund, which is like the very new thing. So a friend of mine who's putting a hedge fund in Miami, then she's going to give us 2 people, but they will give courses about hedge fund. So she told me that it's difficult for her to get a permit from the legal department to give the talk because they are afraid that while they give the general concept of hedge fund and what you do, they might by mistake give some of the secrets of the organization because the hedge fund is about making a lot of money from small changes. So they are afraid that these guys, so the legal issues are also going to interview in the legal department. So that's the weak part of the organization. The other problem is societal. We have a lot of information. and we put this information everywhere. So we are using social network. We are putting information, social network, banking, credit cards, eBay. We use computer, smartphone. We put a lot of information. So that's our personal, that's our society wants us. You put so much on Facebook. Everybody knows where you. I don't know those. I mean, Facebook has a lot of information about everybody, and we voluntarily give it. So we give a lot of information to many people. We want online banking. It's fun to have online banking, so we give a lot of information. But also government demands more information from us. So it sometimes becomes more difficult to get anything from the government without giving information to the government. They want more and more information all the time. Some of it they're just checking it. I tried yesterday to fill some form to get some discount from the city. So in order to get this discount, it's unbelievable how much information they want from me. And they say, you give as much information as you can and we'll decide if you get the discount or not. So that's how it is. The life is like that. So it's better not to have too many bad secrets because they are going to be. And then when you have a little bit of information here and a little bit of information here, the synchronized information from all the sources gives a lot of information. So that's the clever people that are trying, the hackers trying to synchronize information from different places. And that enable people to duplicate identity, which is one of the most biggest threats for you. I mean, there are stories of people that were stopped on the highway. The woman was taken and to jail immediately. A 4-year-old child remained in the car because someone stole her identity and did some homicide. So that's terrible. You have to. So never put your social security and date of birth and place of birth in one document, because this one can steal your identity. Okay, so that's what I said. It's not mathematics, it's just life. But we are a club, so we also do things for life. But we are also to blame, not only the society and the government, because we become tired of being careful. So in order, we are using the same password, very simple password, and we don't change it often. So it's very easy for us with people. If they manage to break into one bank, then they can break into another bank because you use the same password for all banks. So you have to be, we trust that some sites say, don't worry, we are very safe, so use that. So if they say we are very safe, immediately I know they are not safe, yeah, because they can never say we are safe, no one is safe. So don't choose simple password. The engineering challenge. So when there is an attack, I have some interesting examples from Israel, but doesn't matter. If there is attack, one of the things that those that make the attack want is that the system that was attacked will not notice that they were attacked. So then they can keep taking out information or install false information. There is a story, I don't know if you read the book or you know the story of Enigma. That was the German way of hide information. And this guy Turing, he managed to break the Enigma, and that was important in order to save England from the end, and the Germans didn't manage to conquer the island. And that was part of it, that they broke the Enigma, but they didn't know that they broke the Enigma. And in order to hide from the Germans that they broke the Enigma, they let them bomb a boat that was going to America, and the people were killed. Because if they would move the boat away from that, then immediately the Germans will understand that they broke the Enigma. So in order, so this, and one of the guys that broke it, his cousin was on the boat. That's the story in the book. The cousin, so, but he had to sacrifice that in order to save the island. So this is engineering way. In order to, you have to put a lot, it's virtual engineering, but also physical engineering. You have to put a lot of ways in order to make sure both ways, the attacker and those that are attacked. The attackers want to hide it, and those that attack want to understand it. And here we come to mathematical challenges. So in the base, all of it is how to protect the information, what to do that information is not. But you put on every information, you put some kind of a cover, you protect it. And you protect it with a mathematical formula or mathematical way to protect the information. Then after you protect the information with mathematical formula, some people know the formula. So these are the people that might not be weak. Or if once you do something and there is a password here or something and you write it, so there's a lot of things that you can break it. But the most important is the first layer of the mathematics. So what do we want? In the Middle Ages, when they transferred secrets from one place to another, they needed, they had secret ink. So they would write something with the secret ink on the paper, and then when it gets to the other side, the other side had a chemical that they put on it, and they read what is there. And then, but this chemical was known to all the intelligent people around. So if the husband would know that the wife is sending a letter to her lover, he had the chemical, so he could put the chemical on and the secret would come out. So in order for it to be a secret, the other people should not know that there is a secret coming here. This doesn't work nowadays. There's so many information coming here and there, so we cannot afford sending some person on a horse to the other side to tell the lover you're going to get a letter. So that was the only way because you had to give advance notice, is going to come a secret. So that doesn't happen anymore. So we have to have, so in nowadays we have to have a mathematical way to send a secret in a way that it's known that there is a secret, and nevertheless they cannot undo it. So they don't know the password, but they know that some information are coming now. So that's a challenge. So the ink system is not working anymore. We have to have something else that the information is passing by, but no one can take it. For example, let's say that I want to send someone some military information. So I don't send the military information and say, tomorrow we are going to bomb Iran. They don't say it. Instead of that, they write 4, 5, they write some big number, huge number, 51 digits or something, big number. And the other side gets it, they know how to undo it to see tomorrow we are going to make a bomb. So of course there should be some clever mathematics that I see the numbers and I cannot undo it, but the receiver gets the numbers and he can undo it. So this kind of what is here? The hiding system is called crypto system. That's the word we use for the hiding system, the mathematical hiding system. So it's publicly known that there is a hidden information passing by. Nevertheless, you cannot do it. So this is a mathematical challenge to find a way that only I, the receiver, can undo. So here we come to mathematical aspects. So I'll tell you what a current encrypting system is. Why do we need a new method for cybersecurity? And then group-based crypto system. And last time we did the geometry crypto system. But we can do other 3 or 4. We did 4. Okay, so what are the current encryption system? And then, of course, you would ask yourself, why do we need a new one if this is working? And in fact, the encryption system that is having the property that the information that passes by is public, but no one can do it without some trick, is called PKC, Public Key Cryptography. There is a key that the sender and the receiver have some key, and it's called PKC. So the idea of PKC was invented by Martin Hellman Reifmerkel and Wilfred Diffie in 1976. And they had one kind of a type of that PKC, but I say they invented, but it's actually not invented. Considered that we have to have something like that. And what will be the properties of such PKC? So the main thing is one-side function. I'll explain to you in a moment what it is. So the crypto systems that are known are with elliptic curve, the discrete log, and RSA. So RSA, based on number theory, one is based on geometry, one is based on number theory, and the discrete log. So the one that based on number theory is more used than the one that based on elliptic curves, because it's easier to use. Everybody can use it. And it's used by the banks all over the world, by the armies, by the government, by credit, everybody using RSA. And this is based, I told you everything is about mathematics. So there is about groups, there is about geometry, and there is a number theory. So I'm going to talk about the RSA because that's the one that everybody is used. And this is, and I'll explain to you in a moment. But before that, I'll tell you what is the PKC. How does the regular PKC, the steps of the PKC. So we always say Alice and Bob. That's what we like to say. So Alice wants to send secret to Bob. So Bob creates a public key known to everybody. Bob creates also a private key known only to him. Alice encrypts the secret using the public key, and Bob decoded the secret using his private key. So the public key and the private key that were invented by Bob is known. Then Alice uses the public key. She takes her number. Let's say she wants to send a number. She takes the number, she encrypts it, she does something to it, and sends another number. Not the number that and Bob knows to decode it using his private key. So that's not immediately understood. Because she's using a public key and Bob decodes it. So everybody could do it because the public key is known. But that doesn't mean that Bob is interested. He's only interested what he gets from her. So the ingenuity is that in spite of the publicity of the transferred information, only Bob can decode it. And so it means it's based on an action. Here there comes the mathematics. Based on an action that is easy to apply, but very difficult to inverse. So that's the problem. That's the trick. Alice is using something that is easy to apply, but very difficult to inverse without the private key. There's still a mystery. I'm sure you still don't understand. But for example, I'll tell you what does it mean a function that is easy to apply, but not easy to do the inverse. Let's say we take two numbers, 10 digits each. So 10 and 10. We multiply 10 and 10. We get maybe a number of 25, I don't know, digits, maybe 22 digits. We get some number very big. Now, if I give you this number and I tell you, tell me what are the two numbers that gave this number, it will not take half an hour. Let's say that 10 times 10, you do it a few times, you get confused, 10 times 10, in a half an hour you will do it. But to do the reverse, it's very difficult because you don't know even how to start. You start with a number, you say, okay, I'm starting with half of this times 2, it should be prime numbers. Do prime numbers, not more regular prime numbers. To take two prime numbers, so it must be two odd numbers that you multiply, and you want to know what are the two prime numbers that gave it. Very difficult. Computer, of course, can do it. There is algorithm how to do it. You try all the numbers. That's how the computer does. Tries all the number till the square root of the number. That's how it is. Till the square root, and then two numbers up to the square root. It's almost the number. You try all the number. It can take 2 months even to a computer, so it's not relevant. After 2 months, the secret doesn't exist anymore. So. And this is actually, the RSA is the 3 letters of the 3 people that invented it. So in 1976, the idea of PKC with Bob and Alice was considered, but you had to find this one-side function. So they found this one-side function, the 3 guys, 1978, April, and it was a Jewish holiday in the evening, so they said, okay, let's meet in the morning because for a week we don't see each other. But then during lunch they had this idea, so they said, no, we have to finish it. But my wife would kill me, we have to finish it. And it's based on a mathematical theorem that was proven 300 years ago. So you know Fermat's last theorem was a very famous theorem that was proven about 20 years ago, and it was Fermat wrote in his books, I can prove that there is no x, y, and z such as x to the power of 3 plus y to the power of 3 equals z to the power of 3. We know to the power of 2 there are all triangles give us x squared plus y squared equals z squared, but we don't have it with the power of 3. So he said that's an easy theorem. I will write it in the morning, and he never wrote it. And 300 years people tried to do it, they didn't succeed. But he had another theory, that's called Fermat's last theory. In the end, someone proved it. I think that he didn't have a proof, he just thought that he had a proof, but he didn't have. But he had another theory, which is called Fermat's little theory. And based on this theory, this crypto system is based on that theory. So what are the keys? I don't see from here. So do you mind if I sit here and tell me? Okay, so the receiver chooses public key as follows. First, he chooses 2 large prime numbers, P and Q. You remember that P times Q is easy, but to present it as a product is difficult. So the receiver, Alice, in this case, she chooses public key as follows. She chooses 2 prime numbers, P and Q. Then she calculates P minus 1 and Q minus 1, which are P minus 1 and Q minus 1 are not public and not prime numbers. She chooses that. Then she chooses a number E, which is relatively prime to P minus 1 and Q minus 1. So let me give you a small example. Let's say that P is 7 and Q is 11. P is 7 and Q is 11. So so these are the 2 numbers. P minus 1 to Q minus 1 is 6 times 10, is 60. And then she chooses a number E relatively prime to 60. So a number relatively prime to 60, that can be 7. Maybe 7 is the smallest, 7. So the public key that everybody knows is the product PQ and 7. But the public don't know what is P and what is Q. They know only the product and the number 7. These are the public. So then she chooses a private key that no one knows, a number D, such that DE equals 1 when mod P minus 1, Q minus 1. Now, she knows what P minus 1, Q minus 1 is, but no one else knows because she knows PQ, but the public only know the product. So she knows P minus 1, Q minus 1, and she chooses something that mod P minus Q minus 1 D E equals 1. So let's go to the example that I gave before. If P, we said P is 7 and Q is 11. So P minus 1, Q minus 1 is 60. We chose 7, which is relatively prime. Now we want something that 7, something to, it's like the inverse of 7 in this product. 7 times something will be 1 in P minus 1 Q minus 1. P minus 1 Q minus 1 is 60. So if we want something that will be 1 mod, so it should be 61 or 121 or 181. But we want something that is 7, that divided by 7. So let's see, 61 is not divided by 7 because we chose 7. 121 is divided by 7, also not divided by 7. 181 also not divided by 7. 241 is divided by 7. 241 is also not divided by 7. Then the next one is 301. Or, yeah, that's divided by 7. 301 is 43. 343 times 7. We have to take computers now. 43 times 7 is 301. Right? Okay, so D, she calculates D. It's calculation. It's not a choice anymore. D, I calculate, is 43. So the private key of the receiver is 43. So she has a number 43. Now, these are the keys. So some remarks that I say again. N is public, but not P and Q is not public. In spite of the fact that N and E are public, D derives from N, E, and D is private as it's derived from the factors of N and not from N. So D is private. E is public, but D is private. In principle, one can discover P and Q. So the enemy can discover P and Q, but it will take a long time, so it's not relevant. So if we have 21, we know it's 3 times 7, very easy, but a big number is difficult. So the factorization of a number to product of 2 times is an extremely long process. Okay, so how does the process of sending the information? So you remember Alice she knows P and Q, but she only advertises N and E. Now, the sender wants the secret number M to send to the receiver. That's the secret that we want to send. So M should be smaller than N and relative prime to N. That's not important. So the sender encrypts M using the public key E and N. What does he do? He takes M and he does M to the power of E mod N. E and N are public. M to the power of E mod N. Let's say that the number, or the example that I gave, E is 7. Let's say that M is 2, that she wants. M is smaller than N, relatively prime to N. And M is 2. So 2 to the power of 7 is 128. 128. So, but mod N in this case is 60. N is, N was 7 times 11, it was 77. N is 77. So 128 modulo 77, you take out 77 from this. So 128, you take out 77, you get 23 and 28 is 51. So you get 51. So she sends 51 and he gets it. She sends 51 and he gets it. Bob gets it. Bob takes the 51 and he uses the public key N and the private key D to calculate C to the power of D mod N. Because she has D, right? She knows D. She's the only one that knows D. Even Bob doesn't know D. When he does it, m to the power of p mod n, he sends this, what did I say, 53 or something else. He sends 53, he doesn't know D, but she can take D, and she uses an Euler theorem, and she takes the number that he sent her, C, she does C to the power of D mod n, and by Euler theorem, this is M. So we have to prove this theorem here. I mean, we have to believe. It's not a difficult theorem. I mean, first year student cannot do it maybe, but they can follow the proof. But maybe we don't do it here. I just want to explain that even though Bob didn't know D, he does something, but because she has D, C to the power of D mod n goes back to Bm. Because ED is 1. But he doesn't know it. He doesn't know P and Q. He only knows P times Q. So I did, I did by heart. I took a smaller example, but here I wrote a bigger example. Let's look at that example. So the receiver chooses two large prime numbers, 11 and 17. I'm just repeating again what I did. The receiver calculates 11 minus 1, 70 minus 1, we get 160. Or before I did 60, so that's another example. The receiver chooses E to be 3, which is relatively prime to 160. The receiver, it's again the same all the time, Alice calculates D to be 107. Why? Because 107 times 3 is 1 modulo 160. 107 times 3 is 321, which is 1 modulo 160. That's a little bit bigger example than I said before. This I couldn't do by heart. The public key of the number n, which is 187, and E equals 3. The private key that she calculates is 107, but only she knows 107. 11 times 187 is known, 3 is known, she knows what is D. Now let's say the sender wants to send the number m equals 72 to the receiver. So the sender encrypts 72 using the public key 3 and 187. So C, 72 to the power of 3, that's that number, mod 187, you get 183. You know what is mod? Mod number? So that's, I should have said it. You should have all the time, ask all the time, not too late. In mathematics, you cannot have a whole. Mod is, it means what is left after you take full multiply of that number. So let's take a small example. Let's say 21 mod 5. 21 mod 5 is 1, because you have 4 times 5, and you're left a 1. But you take 27 mod 5 is 2, because you take 5 times 5, left 2. 33 mod 5 is 3. 38 mod 5 is also 3. And 43 mod 5 is 3. So you take, it's like when we learn to divide. You take the number, you divide to 5, and you see what is left in integer number. How do you call in English this, what is left? Remainder. So it's the remainder in a division. So she does the same. This is an example that I wrote at home, so I had a little bit more time, I could do the numbers. But what I'm going to do, if I ever show it again, I'll take the smaller number that I do, because then we can calculate it again. But anyhow, the public send 183. So that's what I said. The secret is going there. Everybody can, in principle, find 11 and 17, find D to be 107 and calculate it. But it's so difficult that they don't do it. The public key and the private key D07, she calculates and she gets the message 72. She does this calculation, she gets 72. Okay, I just want to make it again. The same public and private key can be used for many transactions. It's not that you choose new numbers all the time. Every time you do it on another number. But it doesn't have, the secret doesn't have to be numbers. The secret can be also letters, words that you attach to each letter you attach a number. So if you are sending certain numbers, then you can find all the numbers and you know what the word is. It's common to choose, that's commonly known to choose, E to B 65537. But every time someone is breaking it with a computer or something, or they try a lot of times, and then they take a bigger number, and then everything collapses, and you have to start, it takes years sometimes. That's why they are very happy whenever they find a new prime number. We know prime number doesn't divide by, only divide by one and by itself. So, but we don't know all the prime numbers. There are infinite number of prime numbers, it was proven, but we know numbers till 52 digits, but it could be 100 digits, we don't know the numbers. So people are working hard to calculate. How do you find a new number? You take the number, you try to divide by all the number below, but there are many numbers below, it's a very long number. So it takes time to find you, but every time they find a new number, they take a new n. They use this new number, everything becomes more difficult. So when there will be, so now comes, why do we need a new crypto system? Because everybody, maybe you heard about it, everybody is working on a quantum computer. Unlike the digital computer that is made by electrical activity, at the end it's electrical activity, 1 is 1, 0, it's electrical activity, even the phone, everything. The quantum computer, you're okay, right? I'm sorry. The quantum computer is based on quantum system, physical entity, which is quantum, and there are in the quantum system, it relates, two quantum systems relates to each other, and then you get another result. So this quantum system that relates to each other, this, if when the quantum computer will be ready to use, then RSA is broken, because by quantum computer, it's very quickly to take a number and to find P and Q. To find P and Q from N is very easy in a quantum computer. That's why I said World War III, because everything will disappear. All the database, all the infrastructure. I mean, it will, people say that no one will, government will stop it, because it's so difficult for them. But, let me go back here. But so we need a new crypto system. The new crypto system should be built on the fact that some kind of operation that easy to do and not easy to bring back, like n equals pq is okay. We know n, we have pq, we know n. We know n, we don't know pq. So one side function, that's what we need. So we are looking for other one side functions, and mathematicians all over the world look. And it could be at the end very simple, because it's probably some entity that we didn't think that from there it will come. The new system, but it's all based on this kind of. So here, okay, I mentioned that the RSA system is working based on two 300-old theorems, the Fermat-Little theorem and Euler theorem. I don't think that now I should prove the theorems, but could be that I'll come to it maybe in the end of the year. You are all doing algebra, all the juniors doing, all the junior are doing algebra, not junior, freshmen are doing algebra.
Which other? Like,
no, those of you who are freshmen are doing calculus. What else are you doing now?
Calculus and next semester, and then linear algebra and Calc 2.
Linear algebra next semester?
Yeah.
Oh, okay, so we'll come to it some other time. It's not it should be based on what you know in the first year, but unfortunately in the United States you don't learn much in the first year. So we will give you what you need. But you have to trust me that this is the case, that at the end you can really using the, okay, let me go back. Remember what she did here. What she did here, she took C, the number, she wants to send C to the receiver, right? The secret is M. The secret is M, but she sends to the receiver, instead of M, she sends M to the power of E mod N. That's what she sends that's what Bob is sending to Alice, to the receiver. And in order from M to come to C is easy. You do M to the power of E mod N, you get C. To come from C to M, you need D. You need a private key D. Because when you do C to the power of D, you remember, if you see here, C is M to the power of E. And you take now C to the power of D, so C to the power of E is M to the power of ED. Because if I put, instead of C, I put M to the power of E, so we get M to the power of ED, which is 1. ED is 1. So we get back M. Maybe I'll write it. So the secret is M. M is the secret. So what happens in the first step? The first step, Ellie sends, no, Bob wants to send M to Alice. So instead of sending M, he sends C, which is M to a power of E mod N. That's what he said. So M to the power of E, and that's the reminder, you say, right? It's called the reminder. Mod N is the reminder after you do an N. So she gets C. And then the second step, she tried to find M. So she does C to the power of D. Only she knows D, because only she knows P and Q. So she does C to the power of D, but C is M to the power of E to the power of D. So that's M to the power of ED. But ED equals 1 mod N. All this is mod N. MED equals M to the power of N mod N. Because ED equals 1 mod N. So it's M. So she got from CD, she got M. Yes?
Are these formulas, are those all constant?
Yeah, everything is constant and positive numbers.
Yeah, so they use that one for every time they're like sending something.
Yeah. So N and E are public. Everybody knows it. M is the secret that Bob sends to Alice. Bob wants to send to Alice. So this number could be, if she gets the number, there is some formula how the number is translated to letters, if you want letters. So this is a secret. So this is the secret. So, but she doesn't send the secret. She sends M to the power of E, mod N. Let's just to make it that it's simple, let's calculate few M to the power of E mod N. So the example that I did, let's say the secret is 20, and E secret is, okay. Let's take the smallest number that I can think of. So N, let's say N is 21, which is 3 times 7, right? N is 21. 3 times 7. So, but the public only knows 21. Of course, 21 is easy to know 3 times 7, so you take a bigger one, but just like that. So E is something which is prime to 2 times 6 to 12. So we choose E equals 5. Because 5 and 12 have no common factor. Prime means no common factor. So E prime to 12, let me write everything. Okay. N is 21, 3 times 7. 3 minus 1 times 7 minus 1 is 2 times 6 is 12. 5 is prime to 12. Now, the secret, instead of what is M, let's say she wants to find M to be, let's say that M is 4. M is 4. So she doesn't send, he doesn't send 4. He sends 4 to the power of 5 mod 21. 4 to the power of 5, if you can do something, 4 to the power of 5 is 16 times 16 times 4. 4 to the power of 4, 5 times 16 times 16.
1024.
1000?
24. Or, yeah, 24.
1024 mod 21. So now if we do 1024 mod 21, can you do that? 210. So it will be 5 times, and 50 times will be 1050. And here is you take 60.
60.
What?
1024 mod 21, right?
Yeah, 16?
Yeah.
Are you sure? So it's, what is the multiple? What is the multiple of the 21?
48.
49?
48.
48. Ah, okay.
It is 60 now.
So it's 16. For, okay. To know the value. Freshman, write it in. So 124 more 21. How do we calculate it? Maybe a calculator can do it, but how we calculate it is 21 times 48 plus 16. So we divided 124 for 21. The result is 48, and the remainder is 16. So this is 16 mod 21. So what she's sending, so this is C. So C equals 16. C equals 16. Okay, so Alice receives 16. Now what she has to do, she has to do C to the power of D. So 16 to the power of D, but we didn't calculate D yet. D is her private secret. So D is the one that ED equals 1 mod mod 12, right? Mod 3171, mod 12. So if E was 5, so what would be times D to get 1 mod 12? So it will be 3. E is 5. If we take, so we need to be 61. E is 5. No, so 5. D is also 5. I do it by heart. D is 5, because if E is 5, E is 5, ED, so if D is 5, so ED equals 25 which is 1 mod 12. If we divide the 25 to 12, we get 2 times and 1. So E is 5, and these also happen to be also 5. These also 5. So let's go back here. So to get D, to get back M, he needs to do C to the power of D. So C, we know that C is, what is C? C is 16. So C is 16, so 16 to the power of 5. How much 16? How much is 16 to the power of 5? You have to use your computer. Mod 21. 16 to the power of 5, how much is it?
1048. You just want 16 to the power of 5, right?
Yes.
Okay. 1048,576.
576. Okay. And now how much it is mod 21?
4.
That's not so good because what was M? M was 4. Okay, good. M was 4. I got frightened for a moment. You know, there are many problems always. When you do mathematics, you count on other people proving different theorems, and there could be a mistake there, and then it's only discovered. Okay, so 6 in mod, it's 4. So she sent her secret. Her secret is 4. That's her secret is 4. She sent 16. But he, from the 16, he got the 4 using this formula. So we did not prove that netter formula, but we know that it's true, and we just checked it on some numbers. So these are almost the very smallest number that I can do. But if it's very big numbers, I can do it. I cannot calculate easily all these. These are things that in principle we could do. I could do by paper. To get 16 times the 5, 16 times I do it, I get this number, and it's divide by, that's the easiest part to get the 4. So she wanted 4, she sent 16 and she got 4. So this is the RSA. The RSA will be broken with a quantum computer. And then when this is done, we will need new results. And now many mathematicians are trying. And I have students in Israel that are trying to find with another entity, not with numbers, with groups, with networks, something to find some formula that one side is difficult and one side is not difficult. And maybe next year, for those that are freshmen, we'll show you something that is working already. We did something with my student in Israel. It was good, but it was actually what we didn't create a new system. We broke a system of other people. So there was a company that they had a system of creating this one-side function, and we broke it. We found it not 100%, statistically 80%. But once 80% of the times, so it means that let's say they send M, so and we try to break it, so 80% of the time, they send 16. 80% of the time we could guess that it's 4. So that's not good. The banks are not using something that 80% of the time can be broken. So the company went bankrupt. We were very sorry, but we are mathematicians. We looking for the truth. And someone said you should have gone to the company and just tell them, give us a lot of money, and then we don't tell. We don't tell, but we did not do that. So I think I'll stop now. We might have, when I do neuroscience,